Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will talk about the exponential distribution. Let's begin. Okay, so here's today's plan, or the plan for this video. First, we're going to discuss first I'm going to show you the expression that defines the PDF, the probability density function, for a random variable with an exponential distribution. Then I'm going to show you an example, a particular case of that PDF. Then we are going to show together, right, a result from calc that will be useful to find the expected value of an exponential, of a random variable with an exponential distribution. Okay, so that's the plan. Okay, so first let me show you the PDF of a random variable with an exponential distribution. Okay, so that's what the formula, if you will, of an exponential distribution, of a random variable with an exponential distribution looks like. Okay, the parameter, meaning the number that specifies which member of the exponential distribution family we're talking about, is just this guy here, beta, a Greek b. Okay, and the region where the PDF is different from 0 is this, from 0 to infinity. Okay, the non-negative real numbers. Okay, and it's going to be 0 elsewhere. Okay, example. So let me show you a very simple example. When beta equals 1, then, right, what we're going to have, let me go back to the expression of the PDF. F of y is going to be just 1 over 1, that's 1, e to the negative y divided by 1, that's just going to be e to the negative y. So we just have e to the power negative y. Okay, and 0 elsewhere. So in that case, f of y equals e to the power negative y, and we know that we will have this from 0 to infinity, right, and 0 elsewhere. F of y will be just 0 elsewhere. Okay, so let me use R to give you a graphical representation of that particular case when beta equals 1, just for fun, right? Let's do it using R. So let me define an object called y1 that is going to be the possible values in this kind of region. Okay, so I'm just going to create a bunch of numbers that live there between 0 and infinity. So I'm going to create a sequence that starts at 0 and ends at 10, and the distance between each of those numbers in the sequence that I am creating is going to be 0.01. Okay? Okay, so let's take a look at what we have. Okay, can you see that? So just a bunch of numbers from 0 to 1. I'm sorry, from 0 to 10 with a distance of 0.01 between them. Now let me create the first part, the first case of our PDF. Let me call it F1. And we are just going to evaluate our function at those points we just created at negative y1. Okay? Okay. Now let me do something similar for numbers that live in the other part of the real line, right? On the other side of the real line, from negative infinity to 0. Okay, so let me call that y2, a bunch of numbers that live there. Let me just do that from negative 10 to 0, and again we are going to have a distance between those guys to be just 0.01. Let's see if I got what I wanted. Yeah, that's what I want. Bunch of numbers between negative 10 and 0 with a distance of 0.01 between them. Okay, so now I have numbers that live on the other side. And now what I would like to do is assigning the value 0 to each of those points, right? Because that's the second part of this expression. Just 0 if they live, you know, from negative infinity to 0. Okay, so let me call that F2, and we're just going to be using that built-in function in R called rep, as in repeat. Okay, so it's going to repeat the value 0 how many times. Length is going to give you, you know, as the name suggests, the length or the number of elements in a particular object that you have created. In this case I am interested in y2, so I want as many zeros as elements we have in y2. Okay, so F2 is just a bunch of zeros, one for each of the elements in y2. So now we are ready. I'm going to I would like to as I said at the beginning, I would like to give you a graphical representation of that PDF, of that particular case of an exponential when beta equals 1. So I'm going to be using that built-in function in R, plot, and the syntax is first you're going to place the values that you want to have on the x coordinate, and then the second object here is going to contain the values that go on the vertical axis. Okay, so now just a little bit of bells and whistles. I would like that graph to be blue. I want to have a line, so type equals L. This guy, it's an L, not a 1, it's an L as in line. And then well, let me make that line a bit wider, thicker, and what else? Let me, for the horizontal axis, I would like to have the following limits. Remember that we are going to be doing this between negative 10 and 10. Those are the values that we created. So that's why we have that x lim, as in the limits for the x axis, and those are going to be negative 10 and 10. Okay, so if everything went well, okay, so we have, as you can see, we only have the first part of the graph that we created for values that are positive or 0. Okay? But now let's add the other values. So let me use that command lines y2, because those are the values on the horizontal, then f2, those are the values that I want on the vertical, and I'm going to be copying and pasting these options. I want the same color, same kind of line, I want that line to be a bit thicker, and that's it. Okay, so let me copy those parameters there. Nice. So can you see that's a particular example? That's what an exponential distribution looks like. Okay, so we can see that this guy satisfies one of those properties that we mentioned about legit probability distributions, right? Legit probability legit probability density functions should be functions that live on the horizontal or above the horizontal axis. The other part, in order to be a legit probability distribution, is that the area underneath that curve must be equal to 1. Okay? And that is the result that we're going to be showing, but in general. That if we have the generic expression that defines the PDF for an exponential random variable with parameter beta, then we're going to show that, yeah, the area from negative infinity to infinity underneath the curve, the density curve, is 1. Okay? Okay. But now we have a graphical idea of what those guys look like. Okay? Here we go. So now we want to show that result. And as I said, the result, and let me go back to what we have here, what we want is to show that the integral from negative infinity to infinity of f of y dy is going to be 1. Okay? So here we go. Result. Integral from negative infinity to infinity of f of y with respect to y equals 1. Okay, so that's what we want. Here we go. Proof. Okay, so let me write down the expression that we have for f of y. Okay, so it turns out, let's be super careful here. We're going to be very specific. Let me copy this. That we are going to be doing this, right? We're going to break that integral into two cases, right? One integral will go from, I don't want that thing, I don't want that point, that's better. Okay, from negative infinity to 0, and if we live there, right, the expression that defines the PDF is 0, right? Okay, so that's going to be easy. Now the second part, what we want is the integral of 1 over beta e to the negative y divided by beta. How's that? Right? That's what we want. We want to integrate that function, but we want the region to be from 0 to infinity. Okay, make sense? Okay, so let's keep going. Now you take a look at that and then you go, I know that taking the derivative of exponential functions, it's easy, right? We basically use the chain rule, right? So if we use the chain rule in reverse, we go, oh, if I took the derivative of e to the negative y divided by beta, the derivative would be e of the something times the derivative of the something with respect to y. So e to the negative y divided by beta times negative 1 divided by beta, right? So we realize that it is almost what we want is almost, the derivative. What we have here is almost the derivative of e to the negative y divided by beta, except for a sign, for a negative sign. So what we're going to be doing is something that I'm sure that you guys have done before in calc, just trying to refresh your memory here. We multiply by a 1, meaning minus 1 times minus 1, that's a 1. So we're not doing anything illegal, right? But by doing this, again, now what we have inside that integral is just, hey, now what we want is evaluate e to the negative y divided by beta, right, from 0 to infinity. And we have a negative sign outside. So let me, let me do that. Let me write that down. Yeah. So square brackets here, and then what we have here is e to the negative, right? The integral of negative 1 over beta e to the negative y divided by beta is just e to the negative y divided by beta. We're going to be evaluating at infinity and 0. Make sense? And we have a negative 1 here, right? Let me write it down like that so we can clearly see it. Yeah? Okay. Okay. So now I want you to see this guy here, and e to the negative y divided by beta when you evaluate at infinity, and then we go back. Oh, I see. Say for instance that beta was 1, then in that case the graph looks like this. So we can see that as y goes to infinity, e to the negative y divided by beta is going to 0, right? So that guy, when we evaluate this at infinity, that's just a 0. So let me write that down there. So what we have is negative 1 times 0 minus e to the minus y divided by beta, but evaluated at 0 is just e to the 0 power, that's just 1. And finally what we have is negative 1 times negative 1, that's just a beautiful 1. So what we have shown is that, yeah, that expression that we have for the PDF of an exponential distribution is a legit PDF. The curve is always on or above the horizontal axis, and the area underneath is 1. Okay? Okay, so we're good. Let's keep going. So next item in our agenda, we would like to find an expression, a generic expression for the expected value of a random variable with an exponential distribution. Okay, so let me go back to our lecture notes here. So as you can see, there's a nice formula. If we know that we are dealing with an exponential distribution, with a random variable with an exponential distribution, we can quickly find the expected value with that formula. It's just beta, right? And now let me just say something about that. In some other textbooks, they use the parameter lambda instead of beta, and they rewrite the PDF like this: lambda e to the negative lambda times y. Okay, so at first when you see that expression in another textbook, you go, you know, Al, I like that one better. That PDF looks nicer. But if you were to use that alternative expression for the exponential distribution, the price that you would have to pay is that when you compute the expected value, instead of getting the parameter of interest, you have the reciprocal. So in that case, it would be 1 over lambda. Okay, so that's why the authors in our textbook use this guy, right? The PDF looks slightly uglier, but the expected value coincides with the parameter. Okay? Okay, so let's show that the expected value of a random variable with an exponential distribution is beta. Okay, let's show that. Okay. So we can call that a theorem or a result. Theorem. And here we just are going to provide a proof of the first part of that theorem. We are only going to show that the expected value is beta. If you want, later you can try on your own, showing that the variance is given by this expression, beta squared, which is also a nice expression. You guys agree? Okay, so here we go. Proof. Well, how about we start with the definition? Okay, so by definition, the expected value, as you guys know, for a continuous random variable will be the integral from negative infinity to infinity of the PDF. And we use, as you know, the letter lowercase f to denote the PDF. Okay, so as we have seen before, the chunk that matters is the one that lives on the well, the one that corresponds to the non-negative real numbers. Okay, so meaning from 0 to infinity. But let me here be super specific. We're going to write down the other part, the one that is 0, from negative infinity to 0. And now let's write down the other one that is more interesting, from 0 to infinity. And we know that that guy will be just 1. Well, first it's the expected value, right? Oh, and I'm forgetting something here, right? Y times the PDF, right? So we will have here y times the PDF, 0. In that case we're going to have a 0, right? But in this case we have y times the PDF. The PDF here will be 1 over beta, 1 over beta e to the negative y divided by beta. Right? Okay. Nice. Now, no more typos, right? Okay. So now, take a look at this expression. When you see this one, you go, hey Al, that one looks similar to the result we just showed, right? The result where we showed that the PDF of an exponential distribution is a legit PDF, right? So if we had to integrate this, we would be able to do it. We just did it, right? And this one here, well, oh, but if we took the derivative of that guy, that's easy. So when you see something like this, right, immediately that reminds you about something that you've done before, integration by parts. So let me remind you what the formula for integration by parts looks like, and then we are going to use it here. Okay, integration by parts. Formula looks something like this. So integral of u dv equals u times v minus, we have another integral from v, well, the integral of v du, right? Okay. Remember, you've seen it before. You have used that before in your calc courses, I'm sure. Okay. So anyway, so the only one that survives, the only one that is important to us to find the expected value is the second one. So let me copy paste that one, and then using our formula of integration by parts, we will have something like this. We could integrate easily this guy, right? And if we took the derivative of this guy, that would simplify, right? The derivative of y is going to be 1. So let's see if the following proposal works. If we end up, after we apply integration by parts, if we end up with something that is easier for us to solve. If we end up with, after the application of the integration by parts formula, we end up with something uglier, something that is more complicated than what we had in the first place, then we have to try something different. Okay, so here's my proposal. I propose this. dv is going to be this guy, dy. And if that's the case, right, then v would be minus e to the negative y divided by beta, right? Let's check. Derivative of minus e to the negative y divided by beta, minus 1, that's just a constant, so we would have the derivative of e to the negative y divided by beta, that's e to this times the derivative of the exponent with respect to y, that would be negative 1 divided by beta times that negative 1 that we already had, it would be this guy. So it seems that it's okay, right? Okay. Now, we said let's then set u equal to y, and if we do that, then clearly the u would be dy. Okay, so using our formula of integration by parts, right, using integration by parts formula, let's see. So we would have u times v minus the integral of v du. So u times v would be y times negative e to the negative y divided by beta, right? Okay, so let me write that down, and we will have to evaluate that from 0 to infinity. So let me find what I want here so I can write that down. So negative y e to the negative y divided by beta, beta, not b, beta, and we want to evaluate that here, 0 and infinity. Okay, nice. Then minus, right? And then we have integral of v du. So v would be this guy, and u would be this guy. So we have integral from 0 to infinity of this guy times dy, right? No mistakes? Okay. Now, it turns out that mathematicians can show you that when this guy goes to infinity, just think about this factor in this multiplication that we have. So think about the second factor that defines this multiplication, e to the negative y divided by beta. So when y goes to infinity, e to the negative y divided by beta goes to 0, right? But this guy here, minus y, it's going to negative infinity. So mathematicians can show you that this guy, the exponential, goes faster to 0 than this guy will go to negative infinity. So in the end, the limit of that product will be 0. Okay? So let me give you a numerical argument, if you will, that this minus y e to the negative y divided by beta evaluated at infinity, right, or when y increases without bound, will go towards 0. Okay, so here we go. Let me use r to make my numerical argument. So we have done something like this before. We have defined a function in r already. Let me remind you how you do that. So you could use the equals sign or the arrow to make that assignment. I'm going to be creating a function g, and g will be the product that we are interested in. So it's going to be a function with a parameter y, so defined like this, minus y times e to the negative y. So I'm just going to be doing this for the case when beta equals 1. Okay? Okay. So I have defined that function. Now what we want to do is we want to see what happens with that product as y goes to infinity, right? And what I said is that that product will go to 0. So let's see, and let us start with something small, 10. So when we evaluate this function at 10, it's already really small and close to 0. How about 100? Wow, that's really, really small. How about 1000? for any practical purposes, is just 0. Okay, so this guy, that product evaluated at infinity, 0. Okay, then when we evaluate at 0, it's going to be minus times minus, that's a plus, but this guy is going to be 0 e to the power of 0, that's just 1. So that first term is just a beautiful 0. So we have a 0. Let me just type it there. Okay, now when we see this guy, we go, oh, we almost have that one, right? If we had a 1 over beta here, it's done. So since we need a constant there, let's multiply by a1. Okay, so let me do that. That's a very typical trick from calc. Let me multiply by beta, it's just a constant, and then let me divide by beta. So that's just a beautiful 1. But now it turns out that what I have inside this integral, right, is something that I can integrate. Or even better, what I could do is the following. Minus times minus, that's a plus, that's a beta. And now let me remove that negative sign that we had here. So what I'm going to be doing is something that is very popular in statistics, something that we statisticians do very often. We go, oh, guess what? What you have inside that integral defines the PDF of an exponential with parameter beta. And since that guy is a legit PDF, when you integrate it from 0 to infinity, that's just 1. We actually showed that. So what we end up with here is just beta times 1. Which is just beta. So we have shown that the expected value of a random variable with an exponential distribution is beta. Okay, and again, the argument that we used here was that this integral is the integral of a PDF, okay, a legit PDF, over the region where it's different from 0, so we know that this is going to be just 1. And in this case we had already shown that. Okay, so let's summarize what we did today. In this video, what we did was introducing a new random variable, a variable with an exponential distribution. We talked about the PDF. We showed that PDF is a legit PDF, meaning that it's a curve that it's on or above the horizontal axis. We showed that the integral underneath that curve is equal to 1, and then we showed that the expected value for a random variable with an exponential distribution is beta. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.